Yep, thank you so much. And so yes, I am Wesley Bantugan, and I'm going to be giving a presentation on Qiskit. And so a little bit about myself, as I asked a little bit before about what type of codes we all use. I am a Python coder, and so I personally enjoy it a lot for its ability to be able to use displays and different things like that, and that's something which I'm interested in what I'm going to do in the future. And then about myself a little bit, I am a twin. On the right, you can see myself, along with the left is my twin. And so I have a little bit of experience being duplicates, which is ironic because I'm giving a presentation about quantum physics. And so just as a background as well, I have been learning quantum physics for a long time, for the last 7 years, which is long for me. And it just started when I was given a textbook by a middle school teacher, and I decided to just scroll to the back because I'm a nerd, and then I've been just enveloped in quantum physics since then. And so about the program itself, I am going to be doing Qiskit. This is just a quantum simulator. And so anyone who has ever heard the word quantum, you're immediately thinking about something that's very complex. And naturally, it is quite complex. And so this program just allows you to create a quantum computer on your own computer without having to build it, which requires you have to shield it, you're going to have to protect it, and it requires a lot of very expertise. While with here, you can just simulate the actual what you want a quantum system to do, and it makes it a lot simpler and more accessible. And that's the main thing about why I'm drawn to this program, as well as the fact that Qiskit provides resources. The website has a textbook, which is able to allow and guide you through the whole program itself. And this is something I myself have been using to get into quantum programming, because as a field in general, it's very hard to break into because there's so many complicated facets. So having a textbook to be able to follow is actually really useful. And so that's what I've been using in general. And so today I'll be just telling you guys about why are we using quantum computers in the first place, what's the point of them, and then I'm going to give you guys some context to make sure we're all on the same level of understanding, and going to introduce the program itself, and then afterwards I'll talk about some applications and a glimpse into the field itself and what are some things that might be holding us back. And so to start, the differences between classical and quantum computing. Classical is just like what you guys have in front of you, your laptops, your iPhones, that's going to be a classical computer. While a quantum computer, this is a little bit different. With classical computers, you guys are having wires that turn on and off. These are bits that are zeros and ones. By contrast, in quantum computers, we have qubits. These could be a 1 or a 0, but it could be a negative 1, could be a negative 1 over root 2, could be a 1 over the square root of 3. It can be a whole bunch of different probabilities, and that's what makes quantum physics and quantum computing so much more powerful, because they're not just limited to a 1 or a 0 and you can only balance between the two. Instead, you can go to a value in between those or outside of that range, and that opens up a lot of doors to make things faster and more interesting. And so moving on from that, I also want to dispel some quick myths that happen whenever you're thinking of quantum computers, because often in fiction and things like that, you'll think of quantum computing. Suddenly, it's this new device that can do a whole bunch of random and very science fiction-y stuff. Realistically, quantum computers cannot do that. A quantum computer can only do the things that a normal computer can do, but faster. And so it's only limited to what is reasonably able to be done. Anyone who has taken a computer science class in here would have heard anything that can be done in a reasonable or unreasonable amount of time. Same limitations apply to a quantum computer. It's just that now there are more things that can be done in a reasonable time. And that's the main advantage of quantum computing, is some things that are just, you cannot do in a classical computing, things that take longer than the length of the universe to solve, a quantum computer can do in a day. And that's the sort of speed up and advantage which we get from quantum computing, and why it's a field to begin with, is that sort of speed up and that advantage you can get from computers. Okay, so to start, I just want to give a quick poll from you guys. Who here has heard about a logic gate in computers? A pretty decent amount, yeah. And so as a basis of understanding, logic gates are just what is the basis of all computers. This is what determines if if a wire is on or off, and things you can change about them to be able to allow a computer to run itself. And I want to make sure we're all on the same page in this, because that's the basis of Qiskit, is we're using different gates to be able to make different sort of algorithms or things like that I'll get into later. But first, think about bits as just like activating a light bulb. Something is either on or off. And so if it's off, it's represented as a 0. And so naturally, you can think of a light bulb. It's off, nothing's going through it. And then alternatively, if it's on, the light bulb is on. You can think of it as that circuit is active, whatever way helps you. But those are only displayed as 1s and 0s. And for the most part, that's all we'll be sticking to today. And so just to be able to make things easier, the first gate I'm going to introduce is the simplest gate we have. It's called a NOT gate in classical computing. And then all I'm going to teach you guys is it's called an X gate. It does the exact same thing as you would think. It's not whatever is put in. And so, for example, if you are given a 0, what's the opposite of a 0? A 1, yes. And so, using a NOT gate, it's represented, I'm going to be showing today and throughout the presentation, it's represented as an X. It just shows that past this point, it's the opposite of whatever was put in. Make sense? Pretty straightforward? Great. Now we're going to get a little bit complicated. And so the next level, which I'm going to teach you guys, is what's called an XOR gate, or a CNOT gate. And this is where you have 2 inputs. The input, yes? What would be the opposite in the quantum model? The classic model is either yes or no. Because it's not what, you know what I mean? Yeah. For today, we're just going to be dealing with bits, so it'll just be the opposite of 1 is a 0. It's going to be the same thing for both of them. Later down the road, I'll introduce you guys to a 1 quantum thing where we'll start to get into that. But ignore for now like negative possibilities or things like that. It's just, it can be a 1 or a 0. That's going to be it for now. So the opposite of a 1 and 0 is going to be the same. Same thing for quantum physics. Yeah, we can get into that later.
Maybe you could save your questions to the very end. There'll be a quick Q&A session.
Okay.
And just because we can't really hear all.
Yeah, it's all right. Yeah, we'll get to quantum. We'll get to questions later. But anyways, first, the next gate we'll introduce is just called an XOR gate, also referred to as a CNOT gate, is what I'm going to be calling it, which is just called a CX because we are very creative people here. And so in classical computers, you have 2 inputs. This can be a 0 or a 1, and they're going to be on 2 separate wires. And if only one of them, or in this case, to generalize, if it's odd number of them are true, that means they're 1, then the output will be 1. Otherwise, it will be a 0. And so in quantum computing, we don't really have the flexibility to turn 2 lines into 1. And so instead, these are denoted in 2 different lines. There's one that's called a control bit, and one that's a target bit. The control bit is the top one. It's going to be the one that's filled in. And with that one, it's just the second line that's being compared to. And then the second one is the target bit. That one is changed to be whatever is the output. And so if the output is supposed to be a 1, the bottom line, or whichever one is not filled in, turns into a 1. And so that's a little bit confusing, so I made a table that sort of helps explain it. If you notice, these 2 tables are the exact same. So you don't need to flip between back and forth finding some sort of change. They are not. I copy and pasted. And so as you can see, if both of them are 0 or both of them are 1, we aren't going to get more than 2 lines, so you don't need to think beyond that. If they're both 1 or both 0, it's going to be a 0. And if only one of them is on, it's going to be a 1. Pretty good? Okay, let's test you. Not yet, though. So first, this is just the visual example, if you remember with the light bulb. Normally, it's helpful to be able to have two things that come out because you have two things that come in. And so just know that this second input you can mostly ignore because it's just whatever was put in initially. And so as you can tell, if they're both going in off, energy is not going to come out of nowhere, and so the light bulb stays off. But if one of them is on, suddenly a light bulb turns on. And so same thing, if it was a quantum computing, this would be a C0 gate. That's how it looks. But if you notice, it's the exact same thing. The opposite bit is turned on, but the light is still on. Makes pretty logical sense. I hope it does, because now I'm going to test you guys. So this is just an example of a quantum circuit, which I'm actually going to be able to draw for you guys here. And so whenever you're using this system, for now, I am using what's called a Jupyter notebook, which is just splits up the code into different blocks. And so you can ignore this. This is just what allows Qiskit to be able to run in this program. And so what I'm going to do is I'm going to make a quantum system. And so QC, because just like everyone else in the coding industry, I'm very creative with my names. QC is going to be a quantum circuit, and it's going to be 2 digits long. And so, well, there we go. That's going to be the first thing, and we're going to denote that this quantum circuit, I'm going to put a NOT gate on the first line. And then I'm also going to put a C0 gate, which for those of you who are used to classical computing, that's going to be an XOR gate, which is CX, on the second line, second and first line. And then afterwards, we're going to find out what the output is with just measuring what is on that line. So naturally, if you guys look at this code, it might be a little bit confusing to be able to understand what exactly is going on. And that's one thing why I wanted to introduce you guys to what everything is shown as, because something you can do is you can draw out what the circuit looks like. And so if you run this, suddenly you can see what I actually just wrote down. And so now you can just work your way through this. And so as the test, anyone have any guesses what the output of this should be? And to start, everything that goes into a quantum system is a 0. So you have 2 zeros that go in initially. And do we have any guesses what could possibly come out of this? You have 4 options. Yes? 0, 0? That's a good guess. 1, 1? That is also a really good guess. And so I'm going to walk you guys through this to see, so you guys really understand it. So they both go in initially as a 0. But then the first one hits a NOT gate. And so now this top line is 1, and the bottom line is 0. And it enters a C0 gate. And then C0, if we remember, if there are 2 inputs and one of them is on, now the output is going to be on. And then this bottom one is what is overridden with that output. And so now this second line is now on. And this first line is unchanged because that was the target, or that was the control bit. And so if we measure this, the output will be 1, 1. And so whoever guessed that, good job. You're able to follow along. And so hopefully you're able to understand just using logic gates and how we're supposed to be able to use them. And so now that we have that sort of foundation, I'm going to introduce you guys with a little bit of the quantum physics of it. It's not going to be very complicated, but I really want to get you guys into what could be the power of this program. And so what I'm going to introduce you guys is called a Hadamard gate. So a Hadamard gate, basically, it acts similar to a NOT gate, where you have only one input, but then now it's put into what's called a superposition state. Does anyone know the Schrodinger's cat analogy? Yeah, it's a very popular analogy. For those of you who don't know, you are a cruel physicist, and you decide to put a cat in a box. And this cat, a contraption in that device, or a contraption in the box, randomly will kill that cat. Yeah, it's very brutal. But you don't know whether or not that cat is killed until you open the box. And so before you have opened that box, the cat is in what's called a superposition state, where it could be both alive and dead, but you simply do not know until you open that box. This sort of same principle is what's used in what's called a Hadamard gate, where this qubit is no longer a 1 or a 0, it's both. And it could be a 1 or a 0 if you check it, but then while you don't check it, it's both of those positions. And one of the powers of quantum systems is that you could change the probability of it being a 1 or a 0. Or if you're the physicist, you can make the cat more likely to be alive than dead, hopefully. And so that's sort of where this sort of power comes from, is now that you don't have to deal with purely a 1 or a 0, now that sort of frees you up to do some sort of random science with it. And so this is the main thing I want you guys to understand, is now these symbols, you don't really need to worry about it. These probabilities is a 50-50 chance. There's a 50% chance it's a 1, and a 50% chance it's a 0, but you simply do not know until you measure it. And so I'm going to go back here to Qiskit to be able to demonstrate that to you guys. And so if you guys remember earlier, we had this example, and then I can actually code for it to be able to give you guys that table to show what the output would be. But to be able to use the Hadamard gate, all you have to do is you change this to an H. And then suddenly, oops, that is not what I was supposed to do. Now we have an H. And anyone who has done a coding project would know that some things get really long and complicated to be able to make. But one thing that's really cool about this is that that simple change to an H, I'm going to make a simulator with this is just going to show you what the output would be. I cannot spell today, that's okay. Okay. So what I just did was I did a little bit of code to be able to plot this in a table. Because if you guys remember here, I showed this sort of example so you guys could all see what the output is. But then with a Hadamard gate, if we do the same sort of simulation and we run it, oh no, I misspelled something. Yeah, I did not spell back end correctly. That was it. It's all right. Well, either way, if we run that, what the output would be, it's all right. Don't worry about it. I have a backup. If we run this backup, if you remember here, you have the table here, and we simply changed it to an H. And that whole output, what it resulted in, is now there's a 50-50 chance of it being a 1 or a 0. And the thing is, this is the same thing as if you just coded a coin flip. And that was sort of what you can sort of start to see what you can do with this sort of power, is now half the time, the output will be a 1. But then the other half of the time, the output is actually 0, 0, because it's as if the NOT gate did nothing. And then that's sort of what I want to get in, what want to get you guys to know about is that now you have more freedom to be able to play with this. And there's more than one ways you're able to do this. Another way you can do this is what's called a waveform. A waveform is a very fancy way to say, I have no clue what this could be, and so I'm just going to say it's this probability, which is a wave. You can think of like a sine curve or a cosine where it's some sort of wave. It's the same thing. And then if you do the exact same, this is just some code to be able to make a waveform that does the same thing. It gets a 50-50 chance. And the reason why I wanted you guys to really understand that you're splitting up a qubit is because if you do that to many qubits, you suddenly have a lot of power to do a lot of different things. What it's called is exponential speed up. It's because we can speed things up a lot quicker. One thing that is proposed that we could do is, for example, a function to be able to determine if it has one output or if one input has two outputs. Because for a normal computer to do that, you have to test every single output to be able to determine whether or not it's going to be a 1-to-1 or a 2-to-1 output. But then for a quantum simulator, that calculation, which takes a normal computer or the life of the universe to find out, it takes 4 days for a quantum computer to run that and determine whether or not any function is a 1-to-1 or a 2-to-1. And this is then built upon to make a whole bunch of different things. For example, the encryption on your phones or things like that. This is all based on the idea that it takes a computer longer than the length of the universe to determine whether or not two really large numbers have a factor. That is the basis of all encryption on your phones, on your computers, or even here in this conference. An algorithm which any quantum computer can run takes 4 hours to break that. And that would break literally the whole internet because that makes every single thing accessible. And that's the sort of the power and the interest of quantum computing is suddenly you can break everything. And that's sort of why I wanted to introduce this sort of topic to you guys, and so you can do your own investigations about why should we investigate quantum computing? Because we can make and then possibly break a whole bunch of things on the internet, and that's what really makes it interesting. And so there's one thing I hinted at the beginning is that there is some sort of thing in quantum computing which is holding us back, and that's called noise. That noise can be people, for us, you can think of noise as like people whispering in the background, or if you're thinking about Schrodinger's cat, that could be like the smell of the cat. Then you know, oh, that cat's dead, or something like that. The same thing is also true for quantum computers, because qubits are very feeble. Simply background radiation, stuff that we just get hit with every single day, can hit a qubit and then the whole system breaks down. And that is a major problem which is faced by quantum computing, because if simple radiation we face every day can break the computer, you simply can't use that. And that's the big problem which is faced as you get more and more qubits and as you use more of them, it's more likely to face that sort of background radiation, that noise, which could just completely render quantum computing useless. And whether or not this is solved or not is actually something we are approaching but have not yet solved. And that's the line of quantum computing, is whether or not this can become an issue or whether or not it can be overcome. But it's something that's really interesting about quantum computing and sort of what quantum computing is facing right now in the future. And so with that, do we have any questions for me about the whole presentation? It was a lot, I know. And so, yes. Wait, could you repeat that? So, like, how would encryption work with the qubits?
How large is, like, is RSA encryption is stronger because of like larger bit sizes? So right now it's like 10 to the 4 or whatever. How big is current qubit integrity that we have with handling those relative to the size of what we use? What shortest was it? Yeah, how much can it break?
Yeah, and so right now we actually can't break encryption. So the question was, how much can we break with quantum computers? Right now we actually can't really break encryption because the way quantum computers work is they work by what are called algorithms, which are just things that can run some sort of problem and then produce some sort of solution. And we don't yet have the ability to actually break any encryption whatsoever. And the thing that it would actually happen is that if we get to a point where we could break encryption, we actually would have to create an entirely new system to encrypt everything. Because that would just mean we can add like double the amount of numbers to make it a far bigger number, but then the computer it's still the same type of problem. And so we'd actually have to make a completely new type of encryption.
Quantum cryptography relies on like lattice cryptography, but it's not clear exactly what it is or how it works. I haven't seen any talks about that.
Yeah, with lattice cryptography, I don't really have the time to get into that right now. It's just something where you're using a whole bunch of different types of ways to be able to encrypt your stuff.
Is it the same as combinatoric, like where it's proving paths along geometry?
I don't know. You could ask me about that afterwards. Yeah. Yes.
So basically, you were talking about how using qubits and quantum stuff to break through classical encryption. If they finally manage to stabilize quantum, would they then have to use quantum to create new encryptions?
Yes. The problem with how would we have to deal with encryption with the classical and quantum computers is if we break it, we have to use a quantum solution. Otherwise, any quantum computer could break every classical encryption. Yes. I do not know. I believe. Oh yeah, would the slide kit be available to you guys? I believe it should be available on the Scale website possibly, but if not, you can also, the talks are all recorded and you can access those as well. Yeah, yes. Okay, so how do I see technology advancing after we get to quantum computing? My main hope for technology after we've developed quantum computing is to sort of develop alongside it, because quantum computers can't replace what we have. They're too big, and then they require shielding, for example, and different sort of ways to isolate systems that it won't become, I don't believe it'll become widely available to the public, but something which can be used in like supercomputers, for example, to speed things up. But I believe we could build alongside quantum computers to really advance our understanding and maybe make new things in the internet. Do you have a question?
I have a question. Yeah, I understand it can break encryption, but other than that, just like, can you show any algorithms on quantum computers that solve real problems?
Oh, other problems that quantum computers can solve?
Yeah, use reasonable problem, basically.
Yeah.
Algorithms.
So different algorithms, there's a whole bunch of algorithms that quantum computers can approach. Another example which I gave that they can give is when you're simulating, physicists could really use it when you're simulating like particles, for example. It would be really useful to be able to very quickly be able to simulate where would a particle go or things like that. And then with a quantum computer, it could take a lot of those inputs and then could speed it up and also give a better resolution than computers can do right now. And so that's the main advantage of it being able to do what classical computers can do, but faster. And so that's where that comes in. Yes.
Yes. So the quantum simulator, is that, you said it's available for anybody?
Yes, so Qiskit, they have their own, is the quantum simulator available for everyone? It's called Qiskit. It is at the beginning, Qiskit. I'm just gonna scroll up. And so they have their own website. It's their own name, qiskit.com, if you would like to be able to access and download it. It's best used on Python, but you can be able to use it with your own language as well. And it's actually really easy to install. You could just can use a pip function if you know what that is. In the back, yes. How big and how expensive of this? Do you mean quantum computers? Quantum computers are right now very expensive. Google has one which is $1 billion, I'd like to say, but it could be up to 5 billion. It's about the size of this room, is the size of the quantum computer to be able to shield it from radiation. And yes, the quantum computers are very big right now, and so I don't think I would be able to hold that in my pocket anytime soon.
If quantum computers can hack into classical computers to break any encryption, but they're big and expensive, but if they fell into the wrong hands, but classical computers could make quantum encryption, right? So it could hack into classical computers if quantum computers got into the wrong hands.
Yeah, so the question was if classical computers can break into quantum computers.
The
They
question was that they can make good quantum encryption to classical computers.
They can make, the question is whether or not they can make quantum encryption for classical computers. The way it would work, actually, is you would sort of have, the internet is going to be running off quantum computers, and so there would be a way to be able to shield it with quantum algorithms or ways like that. Because there's, right now the way encryption works is you scramble a message with a really big number. And so you do a similar thing, except instead of doing like a really big number, you would put in like quantum probabilities or things like that, where a classical computer that you want to know it could solve, but everyone else could not, if that sort of makes sense. You sort of like shield it in a quantum bubble, I would say, is you shield the message.
So classical computers could protect themselves against the potential encryption of the encryptions on classical computers.
Yes, classical computers would be able to be protected from quantum computers if we make the correct encryption. Yes. Is the Google computer able to break encryption? It is not. And so one thing that's actually really interesting is the computer that Google has is like bigger than the size of this room and is really big and complex. If you Google it, it'll look like some big chandelier. And it actually only has, I believe, 24 qubits is the most amount of single bits that we can able to have running. And so that's sort of why this is useful to have Qiskit, because this can run simple, like a couple of qubits at a time, and that's all we're really able to do right now with physical models, is making a couple of bits. We don't really have that many. To be able to run something like Shor's algorithm, that would take well over that, probably a couple of 100 bits, that we simply do not have access to. Yes. Oh, yeah. Yeah, so whether or not a simulator is able to be run later, that's actually a really good question. If you go onto IBM's website, they actually have a way where you can put in your own algorithm or like your own code, and they will run it on their quantum computers, because IBM has a quantum computer. And so if you would like, you can test something on Qiskit and be like, oh, great, because this is actually made by IBM. And you can be like, this actually works, and send it to an actual quantum computer who they will run it and verify that what the Qiskit gives you is what is expected. Whether or not we can accelerate them, I'm unsure how your GPU would accelerate it, but I believe like you have a better computer, you're able to run programs faster. But if you're sending it off to a quantum computer, obviously you have no influence on it. Yeah. Yeah, so you could have something run faster on a separate computer. Yeah, technically. So whether or not you have guarantee of privacy with the using a quantum computer on the cloud, generally I would think of the cloud as not very secure and not very private. And so even with right now, I wouldn't guarantee you being safe on the cloud if you were to send it up there. Yes. So why are we only limited to 24 qubits? That's because it's one thing that's really difficult about making quantum computers is being able to make sure that it doesn't have any interference. That problem with noise is a very big problem. And also getting it to that state where it's in a superposition is something where you have to have it interact with different molecules. And when you're dealing with things at that scale, it can be very complicated to even get a single bit to become a qubit, because it has to be a specific material and things like that. Oh yeah, in the purple?
Yeah, you made a couple of comments about problems that would take longer than the lifetime of the universe to solve for classical computers. Are you suggesting that quantum computers have the potential to solve Turing and problems?
Whether or not quantum computers can solve Turing problems, things like that, that's a really good question that I forgot to bring up, is that quantum computers can't solve like things that are unsolvable for a classical computer. Because that's the main difference, is that there are things that can be solved unreasonable amount of time. That is things like speed up, one-to-one functions like I named. But then ones like Turing problems, where you're putting the computer into itself, it actually can't solve, because that's something even a classical computer itself cannot solve at all. Given an infinite amount of time, it would never be solved. Same thing for a quantum computer. If you give it an infinite amount of time, it also still will not be able to solve that. Yes? What are qubits made out of? It depends on like the company that's making it, but generally I believe they use silicon or different types of atoms that are used, which are able to easily be manipulated. Yep. In the back. So if there's any resources that you can use to solve sort of quantum problems, the most that I know of is IBM, who publicly have access to be able to, if you go on to, I believe they have a certain site where you can put in a code and then they'll run it. I only know IBM has that. I'm unsure if Google has access to that or anything like that. So I would like to say no, but I honestly do not know if Google has access to it or gives open access to their quantum computer. I doubt it, though. In the back. Yeah. So, yeah. So if there's anything that's already solved with quantum computers, right now quantum computers are still in the realm of classical computers, and so anything you solve with a quantum computer can be done with a classical computer. We haven't yet reached the stage where they're breaking that point. That sort of comes after we approach the problem of noise, because once you're getting to that many bits, then you become, although you're getting more access to more performance, you also have that issue. And so once that's solved, then we'll be able to start breaking the grounds of what a classical computer can do and what only a quantum computer can do. Yes. How did I discover quantum computing? That's how, it's following along how I've been doing quantum physics for a long time. And so just in general research, where I've been looking up random phenomena, it's thrown around a lot, where it's like, hey, quantum computer. And then with the name quantum, I was just like, is that actually a thing, or is that something that's just thrown around? And so that just led down a rabbit hole, which led me here. Yes.
How did we, the people, so like discover qubits and like quantum stuff in general? Did we first, I think that was more like what we were talking
Yeah.
about. Did we first just like make up the word and we're like, oh, this is actually really similar to our word?
Oh, how did we get to like qubits and discovering quantum computers itself? That sort of came with after we started learning about quantum physics and the idea of being able to get something into superposition, some computer scientists were like, hey, could we able to do that for a bit? I can't name off the top of my head who were the first few people to do that, but then they experimented with trying to put a bit into a quantum state, and then from there, after they successfully did that, it unraveled into the whole field.
How did we find out about like quantum physics and quantum states?
So how do we find out about quantum physics and quantum states? That started out with, the earliest I can bring you back to is when we were learning about physics and then we were just thinking about particles in general, back in before Einstein, or after Einstein's general relativity, there was an idea of how like radiation was through what's called a black body, which is just something that can emit radiation, is a way to think about it. But our predictions were wrong, and so after that was approached by different people, if you know like Planck, Heisenberg, things like that, they approached that problem and were able to find out that it's not because, well, it is because physics was actually slightly wrong when you get to really small particles, and it's actually a whole different field, which is quantum physics, where particles have their own laws about whether or not how things can move and things like that. Any other questions? How reliable is it to use for secrets? Right now, it's as reliable as a simple code you could come up yourself. It's not, right now the main focus for quantum computers and like even quantum encryption is sort of getting to the peak where classical computers are and trying to push the field through it. Because there's still problems itself trying to resolve, like getting over 24 bits and trying to make more and more complicated things, and then we're approaching those types of problems. Last question in the back.
Is what's stopping the scaling up beyond 24 bits largely a material science problem, or is it something else?
So what's stopping quantum computing right now? The main thing is that noise problem. It's the noise problem and also just in general funding, because this is something which I'd like to draw attention to because I personally believe we should pay more attention to. But there's a problem with, the main thing is trying to be able to keep that system isolated, to keep it from having background radiation, radiation from itself, and things like that is a really hard problem to solve. And keeping many particles in that state is very difficult because that means nothing can interrupt them. And so if anything happens to them, they break out of their state. And that's something which is a really hard problem to solve. We have a minute for, I think, a couple more. Yeah.
Do quantum computers have assembly language?
Well,
Assembly language that you have CPUs to convert code into machine code.
oh, okay. So what is the like machine language? I'm unsure about that one off the top of my head because it depends on the company that's making it. Sometimes like Google has a different sort of language that they're going to be using for their quantum computers than IBM, for example. And so it depends on the company that's making the quantum computer. Yeah.
How many companies or entities are actually having a quantum computer at this point?
Uh,
There was one where I think it was Elmo had like something quantum computing like was only 7 qubits, but it was also like housed in a tiny drop of acid. So
yeah.
I don't know how big they use to protect it from the other.
Yeah, how many entities are making quantum computers? I'm unsure how many exactly. I know there's many of the big companies in computer science, such as, like as I've been mentioning, IBM and Google have their own, and those are the main frontiers of quantum computing. But I'm sure there's a bunch of smaller companies which are trying to break into that field, which do have their own mini quantum computers or trying to make even their own aspects of a quantum computer that can be put together. And so I'm sure there's a ton of them. Okay, thank you guys so much.